Hello everyone, I'm Ronak Shah and I'm a head of data at Apna. I'm super excited to be here with my colleague Sarfaraz to share more about our journey to the new data platform at Apna. Apna is the largest and the fastest growing professional opportunity platform in India. Job seekers are able to create digital identity through our profiles. And once the profile is created, our job seekers are able to discover and apply to the jobs which are most relevant to them. Last but not the least, our platform allows users to connect with other like minded users through a community product. Since our inception in 2019, we have more than 33 million users on our platform, along with 290K recruiters who are hiring for the jobs across 75 cities. We power more than 3 million interviews a month for 56,000 active jobs on the platform across 40 different industries and job categories. As you can imagine, these 33 million users are not very similar and are quite diverse. They're diverse across gender, across education, across experience, across city, tier, and bunch of different other attributes. But these scale and diversity creates unique set of challenges which we like to translate into opportunities for us. Our AI-powered matching algorithm helps us connect a right user or a job seeker to the right job at the right time. We leverage different markers across all of our candidates with different intents to connect them and make hiring process much more efficient for both job seeker as well as recruiter. But as you know, bunch of these algorithms are not possible without data. At Apna, data is the foundations. Today, we use BigQuery for both our storage and compute as a data warehouse for Apna. Like traditional systems, table schema is defined upfront and enforced at the time of the writing. We ingest CDC and clickstream data into our BigQuery through third-party systems like Mixpanel and Hivo. And this additional layer of ingestion has cost implications along with freshness and consistency challenges. Now, as you can imagine, these different challenges create unique opportunities for us to improve upon over our older data ecosystem. The cost of BigQuery can really go high if not controlled. The time travel limitations and maintaining near real-time syncs have become a challenge for us. And lastly, using a bunch of these third-party systems introduces different point of failures, which creates unique challenges for us to build production-level systems. Like other organizations, we also have very diverse set of users. We have product analysts, product managers, business analysts, data scientists, data engineers, and last but most important, the data products which are built on top of our data warehouse. Most of these users use SQL interface provided by BigQuery to pull their data. There's a growing demand for us to use Spark for our ML pipelines and other engineering use cases. Considering a bunch of challenges which we talked about, we believe that it was a time for us to move on to the next generation data platform. We called our next generation data platform Apna Analytics Ground, which also means fire in Hindi. Our new platform is based on data lakehouse architecture, which allows us to combine the power of traditional data warehouse systems and advanced data lake capabilities. This helps us power our analytics use cases and data science use cases so that we can build next generation of data products. To talk more about our data platform, ARG, I would like to hand it over to my colleague Sarfaraz and share more about our journey there. Over to you, Sarfaraz.
Hey, thanks, Ronak, for the introduction and setting up the ground. Hi, everyone. I will take it from here. So let's try to understand the ecosystem of our data platform. So if you see this image, it's a pretty uh, heavy image over here. and we'll try to break it down and we'll understand it one by one. So let's start from the left and we'll be slowly moving towards the right. Right. So in the left, if you see, so we have our sources, right? So these are basically two sources. One is the transactional sources and one is the clickstream source that we have. So transactional sources for us are Postgres database and MongoDB, and our clickstream data comes from the web and the mobile application, right? So in order to pull the data generated from these sources, we use uh, Kafka connectors for transactional systems, and we have an in-house ingestion service written in Java, which helps us to pull in the data from the web and the mobile and dump into a Kafka topic, right? And for bringing in Postgres data, we use the Debezium Kafka confluent connectors, and for Mongo, we use the Mongo Atlas Kafka connector, right? So these connectors help us to bring the data into Kafka topic. So we get one topic per table. So if you are aware of Kafka Connect, how it works. So let's say if you have 100 tables in your Postgres database, it will create 100 different topics for you in your Kafka that will have your change logs or the or the logs of your transactional systems. Right? So once the data is in Kafka, now we need a processing engine to bring the data into a much more persistent storage for long-term storage or long-term analytics, whatever you call it, right? So here we use Hoodie multi-delta table streamer, right? And so this helps us to bring the data from Kafka wrapping and dump into our GCS location. So we call this first layer as bronze layer, right? And if you see that, instead of mentioning it as Hoodie multi-delta streamer, I have mentioned it as one house because we use one house. One house is building a managed service around Hoodie, and we have decided to use their product to speed up development of our lakehouse. uh, One house basically offers managed ingestion from sources like Postgres, Mongo, Kafka, GCS, and it automatically streams data from these sources into your managed Hoodie tables on GCS or S3, right? um, so yeah, so we use this one to bring the data into bronze. The bronze layer is in GCS in Hoodie format, and this layer is basically a long-term storage, and it is to store data of months and months and years of data. And this is just the raw dump of our data coming in from different sources. So no filtering, no transformations are done over this layer. It is just the exact dump of the raw events that we get. Now, once we have the bronze layer or the raw events, now is the time to give, is the time to make it queryable and meaningful for our uh, analyst or the downstream users, right? So again, so we create a silver tables out of this bronze table, and we use again one house streams for doing that. So now these silver streams are responsible for doing a lot of things actually. So here we do schema validation, timestamp validation, and a lot of transformations like flattening of complex struct fields, maybe deriving new columns, new adding current timestamp values. So all these are done while moving data from bronze to silver. So in case of clickstream, the data is flattened and fan out because the clickstream data that we get is a complex JSON object, right? And inside that complex JSON object, we get events of multiple types. So that's why we have to flatten and fan out from a single stream into multiple stream or multiple tables, right? Um, yeah. So and for in case of CDC, we have to materialize our data, that is create up to date version of the table. All and in case of CDC, all filtering, flattening, this all happens in the silver table before we actually materialize the table. And because so this is one more benefit of having a bronze layer, so that if anything is messed up in your pipeline, we always have that bronze table, to uh, to recreate the table if in case of any issues, right? Like a code logic error, or some schema issues. We don't need to go back to our sources, like from like Postgres or Mongo, but instead reprocessing of data can be done directly from the bronze layer, right? And yeah, so this actually helps us. So now this stream actually creates, so if you have 100 tables, so there'll be 100 streams, and you will get 100 different silver tables in your silver table in your silver layer, right, in GCS. And this stream is additionally responsible for doing few other things, is that for like in case of schema validation, it reads the schema from the schema registry. So we store all our schemas in schema registry. So this stream will fetch the required schema, and or the targeted schema from the schema registry, and apply and do a schema validation check over there. And if it is, and if the records comply to the schema, it will go and write the data into GCS. And simultaneously, it also does an entry to the Hive metastore, and does a BigQuery sync process as well. So so this silver table is essentially exposed as a external BigQuery table in Google BigQuery, so that we can quickly check our data, test validate our data using BigQuery, instead of having the need to write and deploy a Spark job, which is essentially a time-consuming process, right? And the long term, there was a history of that the analysts in our organizations, where organization was much familiar with Google BigQuery. So this having Google BigQuery, in during the migration phase, uh, actually helped us in slowly migrating users, over the period of time. If suddenly we would have moved out of BigQuery and gone to Presto or Spark, that would have created a lot of chaos inside the company. So we decided, we'll still have this amazing facility of BigQuery hoodie sync, and maybe over the period of time we'll keep migrating users to Presto or Spark more and more over the period of time. Yeah. So finally, we have this gold layer, which is created on top of silver layer. So yeah, so we use DBT, in-house DBT, for that. So DBT is responsible to create the gold layer again in hoodie format, right? And we use Presto as an ad hoc querying engine, which can query data from both silver and gold layer. Yeah. So yeah, moving ahead, let's go and try to understand one important thing, is that at the time of your schema validation. Um, so I said that we do a schema validation check, and if records comply to that schema, the data goes into the actual table. But what if it doesn't, right? So in case of that, the records which does not comply to the schema are being moved to a quarantine table. So for each table, you would have a you know quarantine table for every table. Right? And whenever there is an event or a data in the quarantine table, we are alerted, right? And that helps us quickly turn the table and go back to the producer team saying that, hey, you have some issues in your table or in your data. Please fix it, or whatever is the action required. We that helps us to quickly identify the issues, right? It might be schema issues. In case of that, we have to change the schema and backfill the data again. Yeah. So this process actually helps us a lot because having schema issues is a very big pain in day-to-day data engineering field, wherein the data engineering are not aware that whenever a column has changed its data type and have started publishing data in that newer data type, and that may come as a surprise for you and me, and you wake up in the morning and your pipelines are broken, and you worry what went well or what that didn't went well. So yeah, this alerting helps us to solve any issue going forward. Yeah. So quickly, I will touch upon the storage architecture that we have. Um, so yeah, so the bronze essentially is again Hoodie on GCS. Hoodie is internally using Parquet and Avro, right? And there is no user access. When I say no user access, I mean there is no, they only the data engineering team can access the bronze layer, and no other one, no other people can, or no other folks can access this bronze layer. And that data is obviously partitioned on ingestion date. So having partition on ingestion date actually helps us to reprocess data in case of any need. We can go back X number of dates and exactly process those those records from those partitions back in case of any issue. Next is Silver. Again, Silver is Hoodie on GCS, wherein we do schema validation and schema versioning is maintained, right? And there are a lot of file management for better performance queries. We maintain file size. Hoodie file size, file sizing is there. There is compaction running. There is clustering for better query performance. So a lot of file management things are being kicked in here or are running over here, right? And for larger tables, larger tables like which have billions of records, the data is usually partitioned on the date of the let's say any created date or updated dates, right? And finally, the gold, it's an aggregated table like feature store or pre-computed table, which are refreshed on usually on a daily cadence, right? And that actually helps us to avoid a lot of joins again and again, because the data is already pre-computed, and it is fine to have data refresh per day, once in a day. So yeah, so you save a lot of cost by avoiding those heavy joins. And then these are again given a granular access, like a project level access or a team specific level access is given here. Yeah. Going ahead. So let me quickly touch base upon the older architecture. So earlier we used to use a third-party tool known as Hivo. So how this Hivo internally works is that it is to pull the change log and then bulk write into GCS, right? It is to buffer for some time, and then let's say every 15 minutes it is buffering, and then it will bulk write into your GCS location. Now what it has to do, let's say the data in your GCS location, I am referring to at delta records, right? And so this delta records needs to be merged to the main BigQuery table, right? So what it does is that it creates an external BigQuery table on top of that GCS location, and finally does a expensive merge operation between the external BigQuery table having that delta records and the final and the main BigQuery table. So some merge operation like when matched, do an update; when not matched, then do an insert. So these kind of merge operations are run actually to materialize the table or create a fresher or up to date table in your BigQuery. So as a result of which, what happens is that if you want data very often in your very often, I mean, you want data to be you want fresher data to be available in BigQuery, more early, you incur paying cost to BigQuery because you have to run those expensive merge queries more frequently, and that shoots up your BigQuery cost as well. Yeah, so that was an issue with Vivo, and definitely this is the cost issue of Vivo. And then there was no issue of there was no and there was no support for alerting in case of anything goes wrong. So uh, we would lose those data. Those data will be skipped without any acknowledgement or without any alerts until and unless you go and check in the UI, right? So these are the bloat technology which we kind of got rid of. Yeah, and then for bringing the mixed panel data sorry, clickstream data, we use Mixpanel, and Mixpanel is to generate your BigQuery tables, and there goes the join between clickstream data and CDC data to create your dashboards. Right? With a new architecture, it's very uh, straightforward. There is no merge operations going on, right? Everything is done via one house streams, which uses internally uses Hudi multi-delta streamer. So whatever it is done, it has to be done. It's very straightforward, no merge operations or as such. Your data is in uh, only in your data is in GCS in Hudi format, and now you have the choice to plug in any of our technology depending upon the use case, or you get or teams, right? And earlier if there was a dependency on only BigQuery, now you can plug in anything like Spark and uh, let's say Spark or Spark MLlib to gain the full power of ML, right? And to serve our, and then we can use like Presto to derive our analytics and all. Yeah, so quickly touch basing upon the benefits. Benefits that we get from the newer architecture is that the data is almost near real time, right? Um, we can set an SLA, or the SLA basically refers to how faster you want newer data coming in. So this can be tuned for each table. So for very critical table, we can go as low as 1 minute, and for tables which are not critical, we can set it to a 1 day or so, right? So there are less data consistency and data availability issues. And if there are, we have alerts for availability as well. If your data is not getting pushed in or is not getting written quite often as per the SLA, you will get alerts, right? And in case of data consistency issues, as I have already said, there is a process of quarantine alerts as well. So custom alerts and monitoring can be done because as we have Grafana, one house also facilitates you with Grafana, so you can put in all your custom alerts and monitoring. Facility to support SCD2, via help of some external transformers, Hudi external transformers. We now have the support of SCD2 if you want to maintain any tables in SCD2 format. Then decouple storage and decouples architecture, which gives you, with that is like a decouple storage and compute architecture, which actually helps us in cost saving, right? I know if your data volume is very high, you can scale up your compute as well as the storage. But in case of during the night hours or when your traffic is not that high, you can actually shrink some of your clusters to save cost, right? And now finally, we can leverage the power of compute engines like Spark, Presto, and you are not actually tied up to any vendors, but basically it's open source right now. So if there is a need, you can plug in those amazing compute frameworks as per your need. Right? Yeah. So that's all I had. So thank you. Thanks. If open to Q&As. Thank you, everyone.